Okay, pre-calc students, this is Unit 3, Day 3, and I'm going to work through the classwork examples for you. But as always, you will learn these by working through these examples on your own and not by watching me do them. So it's best for you to try the examples first, and then when you get stuck, that's when you can turn to the video. So the first problem we're doing is 19 from the big list, and I see that the left side is more complicated, so I'm going to start on that side. Whenever I see this cosine squared, I'm going to consider one of my Pythagorean identities, and that would be this first one here. So I can replace the number 1 with what the 1 equals, and that 1 is equal to the sine squared plus the cosine squared. So I'm going to replace this number 1 with sine squared theta plus cos squared theta. So I still have sine theta in the numerator. And then this 1 becomes, let's use a new color to replace that, sine squared theta plus cos squared theta. And then I still have minus cos squared theta. And this equals cosecant theta. All right, so when I do that substitution, I have cos squared theta minus cos squared theta, which cancels out. So now I have sine theta over sine squared theta. You can write that sine squared theta as sine theta times sine theta. So then it's easier to see that you can cancel out one sine theta here and one sine theta here, which is going to leave you with 1 over sine theta. Okay, and then this is going to be one of your reciprocal identities, that cosecant is equal to 1 over sine theta. But your final step is cosecant theta equals cosecant theta. Okay, in 25, again, the left side is my more complicated side. So what I'm going to do is I'm going to try to get things in terms of sine and cosine. It's very tempting to keep this secant squared right here because I see another secant squared here. But if I do that, I don't have anything really good to substitute for my sine squared. It's just going to make things more messy if I change my sine squared. So what I'm going to do is take this secant squared, and I'm going to replace that one with 1 over cosine squared. So I have 1 plus 1 over cosine squared theta sine squared theta. And then because I have 1 over cos squared theta times sine squared theta, I can put that together in one fraction. 1 plus sine squared theta over cos squared theta. And then I know sine over cosine is tangent, so sine squared over cosine squared, that's going to be the tangent squared of theta. So I have 1 plus tan squared theta is equal to secant squared theta. And then I'm starting to wonder if that's one of my Pythagorean identities. So let's take a look at that list again. And it is. It's right here. So tan squared theta plus 1, that's what I have, is the same as secant squared theta. So I can write my final step. Secant squared theta equals secant squared theta. Okay, in 29, we've seen problems like this before. Generally, it's a good idea to distribute the first term to both terms inside the parentheses. So now I have cotangent theta tangent theta plus cotangent theta cotangent theta. All right, so in the first one, I know these are reciprocals of each other. You're going to need to change one of these two functions to their reciprocal. So I'm going to change the cotangent to be 1 over tangent. And cotangent times cotangent is cotangent squared theta. So this is going to simplify to tan theta over tan theta which will eventually become 1, and it's tempting to skip all of this, but your format is very important in trig identities, so you need to bring everything down. So finally, I have 1 plus cotangent squared theta equals cosecant squared theta. And again, I'm wondering if maybe that's one of my Pythagoreans. So looking at the list, I see it's the last one. So 1 plus cotangent squared is the same as cosecant squared. So cosecant squared theta equals cosecant squared theta. Check. All right, 93 has a fraction plus a fraction, and these two terms need to combine to make one term over here. So I'm going to have to find a common denominator. This denominator is cosine, but it lacks sine. This denominator is sine, but it's missing the cosine. So what I'm going to do is multiply the first fraction by sine theta over sine theta, and I'm going to multiply the second fraction by cos theta over cos theta. So when I do that, I have sine theta cos theta plus sine squared theta, because I distributed to both terms in the numerator. And this has a common denominator, so I'm going to make one great big fraction. My denominator is sine theta cos theta. And then this cosine distributes to both of these. So I have plus cos squared theta minus sine theta cos theta. And this is supposed to equal cosecant theta secant theta. All right, right in the middle of all of this, I see this, sine squared plus cos squared. That should be the Pythagorean that you are most familiar with. So looking at your list of Pythagoreans here, you should be able to see it right here. So sine squared plus cos squared, that can be replaced with a 1. And then I also have sine theta cos theta and negative sine theta cos theta. So those two just cancel right out. So this whole big numerator has become just the number 1. This one here is replaced with a 1. I have 1 over sine theta cos theta equals cosecant theta secant theta. So 1 over sine, that's the cosecant. 1 over cosine, that's the secant. So I can finally write this as cosecant theta secant theta equals cosecant theta secant theta. Okay, in 47, we are going to need to use our factoring. No, probably not. Factoring is one idea. I could factor this denominator to be 1 minus sine theta times 1 plus sine theta because it's the difference of squares. But I would only do that if that would cancel something out in my numerator, and it doesn't. So instead, I think I'm going back to my Pythagoreans again. One more time, I'm going to take this number 1, and I'm going to replace it with sine squared theta plus cos squared theta. So I have sine theta over sine squared theta plus cos squared theta. And I still have minus sine squared theta. And this equals secant theta tangent theta. So my sine squared and my minus sine squared, those cancel out. And now I have sine over cosine squared theta. Well, my secant is 1 over cosine theta, and my tangent is sine over cosine theta. So it could help me if I were to split this cosine into 2 cosines. So I would have sine theta over cos theta, cos theta. All right, and I need secant to be 1 over cos theta, so I could just make that a 1 sine theta. That would help me. So I can see that the 1 over cosine, that becomes the secant. The sine over cosine, that becomes the tangent. So let's write down the right side, secant theta, tan theta, and then this is going to give me 1 over cosine is the secant theta, and sine over cosine is the tan theta. Okay. All right, problem 137. This is a factoring problem. So when you see a problem that you think might be a factoring problem, it can help you to change your trig functions into x's. So you can let x equal sine theta, so that now what you're looking at is 2x squared minus 5x plus 3. Now one way to factor this is to set up your factor pairs and to guess and check, so you know that 2x squared has to be 2x times x, and 3 has to be 1 times 3, except there's a negative in here, so somehow we have to figure that part out. But another thing that you can do is a method where, let's cross this out, you find two numbers that multiply to the first times the last. So they're going to multiply to 6. And they're going to add to the middle number, add to -5. So numbers that multiply to 6, let's see, I need a pen again. Might be 1 times 6 or 2 times 3, but if I want them to add to -5, it's going to have to be -1 times -6, -2 times -3. So the last numbers, these are the ones that would add to -5. So what you do is you take your middle term, the -5x, and you replace that with these numbers. You replace it with -2x minus 3x. Then you bring down the 2x squared, and you bring down the plus 3. All right, next you split these terms into two groups. So you're going to take the greatest common factor out of the first two. That would be 2x, which leaves you with x minus 1. And you take the greatest common factor out of the second two. So you might think that that would be 3. But if your lead term's negative, take out a -3. And that's going to leave you with x minus 1 again. So then your factors are going to be x minus 1, which is being multiplied by both 2x and by minus 3. So this is the factored form of 2x squared minus 5x plus 3. If you can do that just by guessing and checking, you don't need to do all these steps, but these steps are here to help you out if you can't get it on your own. All right, so I'm going to take all this back now to the sign. And instead of x, I have a sign. So instead of x minus 1, it's going to be sine theta minus 1. And instead of 2x minus 3, it's going to be 2 sine theta minus 3. Okay, looking at the denominator, you have the difference of squares. You have sine squared theta minus 1. Again, if you think about this as the sine squared being an x, you could be thinking of x squared minus 1. And then you can remember your difference of squares pattern. That would be x minus 1 times x plus 1. So going back over here, that's going to be sine theta minus 1 times sine theta plus 1. So these two will cancel, and it looks almost the same, but in your last step you want to make it look exactly the same. So you have 2 sine theta minus 3 over 1 plus sine theta. 2 sine theta minus 3 over 1 plus sine theta. All right. In 77, we're going to try a strategy called multiply by the conjugate. I'm going to write that down. That did not work. Try again. Okay, so if you haven't seen the term conjugate before, the conjugate of a minus b is a plus b, and vice versa. The reason why multiplying by the conjugate is valuable is because if I multiply a minus b times a plus b, my middle terms will cancel out, giving me the difference of squares. So that's kind of like backwards of what we just did with factoring the difference of squares. So in this case, I have 1 minus sine theta, so the conjugate of that is going to be 1 plus sine theta. And the reason I can multiply by that in the denominator is if I do it also in the numerator. So I'm going to take the left side and keep it the same, secant theta plus tan theta. And in your numerator, you want to keep it factored. So let's make a note of that too. Keep the numerator, in this case, factored. Because if it's factored, it's easier to cancel things out. So cos theta times 1 plus sine theta. And then in the denominator, 1 times 1 is 1. 1 times sine theta is sine theta. Negative sine theta times 1 is negative sine theta. And negative sine theta times sine theta is minus sine squared theta. So now you see your sine theta and your negative sine theta cancel out. I have the difference of squares, and I'm going to do a Pythagorean substitution to see if I can get this down to one term. So my left side is still secant theta tan theta. My numerator is still factored. And my denominator of 1 minus sine squared, I'm going to replace the 1 with my Pythagorean sine squared theta plus cos squared theta. And then minus sine squared theta, I'm bringing that down. So the sine squareds will cancel out, and now I have cos squared as my denominator. So this cos squared, one of those cosines can cancel with the cosine up here. So secant theta tan theta. Copy your numerator again. Your denominator, you can write that as cos theta, so that you can watch these two cancel out. Now, in your numerator, if you have 1 plus sine theta, you can split that into two fractions. So 1 over cos theta plus sine theta over cos theta. 1 over cosine theta becomes your secant theta, and sine theta over cos theta becomes your tangent theta. And then you just want to bring down the left side for each one. And you're done.